Okay, so just a quick recap here. So we were talking about conservation of energy, the idea that energy is a conserved quantity, a deep and profound principle in physics. And the setup was we had an isolated system, no energy in or out. And so there are various ways in which nature can store energy, okay, in the kinetic energy of moving objects or in potential energy. Okay, whenever physicists say potential energy, they really mean energy stored in fields, electric field, magnetic field, gravitational field, whatever. So there's kinetic energy and potential energy as the ways in which energy can be stored. And so we're imagining that initially there's some amount of energy E1 stored in subsystem 1 and some amount of energy E2 stored in various forms in subsystem number 2. And now we observe, yes, the energy E1 goes down by a certain amount. The change in the energy of E1 is negative. It's gone down some amount W. Then automatically, by conservation of energy, the change in the energy stored in region number 2 must increase by an amount plus W in such a way that the change in the total energy, that's change in E1 plus E2, is delta E1 plus delta E2, negative W plus positive W is equal to 0. Okay, so that's the idea of conservation of energy. Thought of in terms of ways in which nature can store energy. Delta E total is equal to 0. There's no change in the total amount of energy stored. It can just move from one location to another or from one form to another. Okay? But remember that this is sort of like we're ignoring how the energy is actually transferred from region 1 to region 2 or from one form of energy to another form of energy. Okay? So this is just sort of like an accounting principle. It's kind of vacuous. It has no physics in it. It's just trivial. Okay? And so what we really want to, so far we've talked really about storage. Okay, energy storage mechanisms. Now we want to move to something that's really interesting, which is energy transfer mechanisms. So we said that actually whenever, say, this guy loses 5 joules of energy, well, that increases, this guy gains 5 joules of energy. There's been 5 joules of energy, W equals 5 joules, transferred from region 1 to region 2. And that transfer of energy is always accompanied by an equivalent transfer of mass, that 5 joules divided by c squared, mass transfer as well, because E equals mc squared. So now we want to shift our attention from energy storage mechanisms to energy transfer mechanisms. What are the various interesting and amazing ways in which nature has to transfer energy from one location to another or from one form to another? So we're shifting from energy storage mechanisms to energy transfer mechanisms. So this is energy transfer mechanisms. Okay, and this perhaps the simplest and most common example of the way in which nature can transfer energy from one form to another or one location to another is through this thing called work. Okay, so in high school physics, of course, you've all talked about work. So what I want to do is I want to go through a very, very simple and basic and fundamental discussion about what is work. Okay, because remember, in physics, what we do is we take the simplest possible example and we try to understand it as deeply as possible. So we're going to try to understand this notion of work, because I want you guys, physics majors especially, you should understand this intuitively. It should be completely obvious that work is force times distance, okay? Intuitively obvious. So we'll start with the simplest possible example that I could think of, and that is we've got a block of, say, mass m, and it's sitting on a frictionless surface. Okay, so this is frictionless. And this block starts at rest. Okay, and there's some guy here, and this guy pushes on the block. Okay, so he exerts a force F on the block. And we're going to imagine that that force is constant. Of course, that block is going to accelerate. The block and the person's hands are moving faster and faster and faster. But through that faster and faster motion, we're going to assume that this person, just to make the simplest possible example we can, that this person applies a constant force. Starts at 10 newtons, always maintains a 10 Newton force as the block is accelerating and moving along this x-axis. So we'll say that the force F is equal to constant. Okay, simplest possible example. So what we know, obviously, is that this block is going to accelerate. It's going to move faster and faster and faster. And so after it has moved, say, from some position x initial along the x-axis to some position x final, so here it is later on, further down the line here, this thing is now moving with some speed v. All right? And the displacement, say, of the center of mass of the block is from here to here. And so that will be delta x will be how much the block is displaced. Delta x is the change in the x position, that's x final minus x initial, is that distance. Okay, great. So that's our basic setup. And now we want to ask this question, what is work? Okay, so when we think about work, we think of something like, work is kind of like the effort expended. Okay, so how much effort was put in to, while you're pushing on this block through this displacement delta x, how much work or effort did it take to do that? Okay, so we're trying to ask the question. So the symbol for work is W. Okay, so what is the work done? Well, the first thing we want to, because we want to understand this just sort of intuitively and obviously, so we want to say, well, what could the work possibly depend upon? So we have various parameters here. We have the force with which the person pushes. We have the distance over which that block is accelerated. We have the final speed. We have the mass of the block, and so on. There's a bunch of parameters in here. And so we want to think, well, what could the effort expended depend upon? So first of all, clearly, the work will depend upon, so I'm just using a little squiggly line there. It's kind of like dimensional analysis. You look at a problem and you say, well, what could the answer that you're looking for depend upon? And so, well, obviously, the amount of work, the amount of effort expended is going to depend upon the force. Okay? Because if this person applies a 10 Newton force and accelerates this block through, say, 5 meters, that's a certain amount of effort was expended. If you were to double the force, obviously the amount of work or effort put in is doubled, because to double the force is the same as taking one person exerting 5 newtons of force, put them next to another person exerting 5 newtons of force to double the force. And so obviously the work, the total work done is the work of this guy plus the work of this guy. If you double the force, you double the amount of effort expended. So it should be that the work is proportional to the force. In fact, why don't we just put in a proportionality constant here instead of this? So the work should be proportional to the force. If you double the force over the same displacement, you've doubled the amount of effort. So that should be obvious. What else could it depend upon? Well, it's obviously going to depend upon how far you push this guy. If you just push this guy with 10 newtons force through, say, 2 meters, that's some kind of work you've done, some kind of effort you've expended. But now if you go again and continue pushing for another 2 meters, well, you've also doubled the amount of work or effort expended. So it should be that the work is proportional to the force and proportional to the displacement. Okay? And now you might say, yeah, but it also might depend upon the speed, okay? But also the speed might just depend upon the amount of work. The amount of work you put in and get more speed and so on. So it's not clear that, speed or mass are going to appear in this expression for work. But clearly it's true that the work will be proportional to the force and it will be proportional to the displacement, okay? So then we say, so because work is proportional to force and independently proportional to the displacement, it tells us immediately that the work done, the effort expended, is going to be proportional to the product of the two. So for the same displacement delta x, if you double the force, you double the work. For the same force, if you double the displacement, then you also double the work. Okay, so we're going to guess that that the work done, the effort expended, is going to be proportional to the constant force applied and the displacement over which you apply that force. Okay? And in fact, this proportionality constant is, it could be 2, it could be 5, it could be 1/2, who knows what it is. So it turns out that relativity tells us what it is, and it's actually just equal to 1 times this. So the work is not, 1/2 F delta x. It's not 2 times F delta x. It's actually equal to F times delta x. So that comes from special relativity. So we'll just make this initial guess here. Okay, it's the same. It's what I said before. So kinetic energy is Newtonian approximation is 1/2 mv squared. Where does that half come from? Well, it comes from special relativity. Okay, for the same reason that that's a number 1 sitting there. That's just a proportionality constant of 1. Okay, so this is our initial guess, or sort of intuitively obvious guess as to how much effort is expended in pushing on that block through a displacement of delta x. Okay, so one thing I want you to notice about this, and this is very important, is that if you double the force, you double the amount of effort expended, the work. If you double the displacement, you double the amount of effort expended, the work. If you double both of them, you quadruple the amount of work. This is a very important point. Okay, so if we were to sort of make a little graph here, so we say here is the, can I fit this down here? Let's fit this down here. So here is the displacement delta x, and here is the force that you are applying, the constant force that you are applying. So suppose that you apply a force of this magnitude, so this is 0. You apply a force of this magnitude, and the displacement is this. Okay, so then what we find is the work done, the effort expended, is the force times delta x. That's the same as the area of this rectangle. This is the force you're applying. This is the displacement delta x. And so the work done is force, height of the rectangle, times delta x, width of the rectangle, is area of the rectangle. Okay, so work is equal to area under a force versus displacement curve. Okay, and if you double the force from this value up to this value, and at the same time double the displacement from this value to this value, then force times displacement is actually 4 times as much. Okay, it's this whole area. Okay, so doubling both F and delta x quadruples the amount of effort put in. So it's very important to understand the intuitive idea that the work done is proportional to the area under a force versus displacement curve. So you might guess correctly that if you are exerting a force that varies with the displacement, so let's start with a small force and then exert a harder and harder force as you go. So your force versus displacement curve, might look something like this. Here's force, and here is displacement. It might start off, say, with a small force and then increase. Okay. Okay, then you might guess correctly that the amount of effort expended is actually the area under this force versus displacement curve. And that's what you need to do. This, of course, involves calculus, and this is what you need to do when you're dealing with forces that depend upon the displacement, like when you compress a spring and so on and so forth. We'll talk about that later. But that's sort of an intuitive and very important point. Okay, so the next thing is, well, great. We've thought sort of intuitively about that. It seems obvious that the amount of effort expended should depend upon the force and the displacement. Okay, but is this actually right? Does it make any sense? Okay, so now you go to something else entirely and you try to see whether the puzzle pieces fit together. Okay, so now you do something like this. You say, well, if our definition or guess at the effort makes any sense, well, so work is equal to force times displacement. Well, so what we know from dynamics, we know that the force that's applied is related to the mass and the acceleration, how quickly it's picking up speed, by force is equal to mass times acceleration, okay, times delta x. So dynamics tells us this, basic Newtonian dynamics tells us this, that force is equal to mass times acceleration. But now we also have this expression, mass times acceleration times displacement. So now you might remember that when the force is constant, and hence the acceleration is constant, in one dimension, there's a very simple kinematical formula which says that 1/2 mv final squared minus 1/2 mv initial squared is ma delta x. Okay, so if you don't remember that, I'll ask you just to look that up. So kinematics in this very special case, and we're dealing with a very special case where the force is constant, simplest possible case we can imagine, so we don't need calculus. So kinematics tells us that when the force and hence the acceleration are constant, okay, then this expression is the same as 1/2 mv final squared minus 1/2 mv initial squared. Okay, so it's some quantity final minus some quantity initial. Well, that is, by definition, the change in said quantity. And so we write this as change in. Delta always means change in something, final minus initial. And it's the change, in this case, in 1/2, a quantity called 1/2 mv squared. Okay? And then we think, what's 1/2 mv? That's kinetic energy, or at least the Newtonian approximation to kinetic energy. And so we see, well, this is really interesting. So what it's saying is, so according to our sort of intuitive sort of definition of effort expended or work done, we have work is equal to force times delta x. And when we apply dynamics and kinematics, we find that that's actually the same thing as the change in the kinetic energy. Okay? And so then we look at this thing and say, does that make any sense? Well, let's see. So what is it really saying? It's saying that when we apply some force F through a displacement delta x, we've put in some sort of effort. And what's the effect of that effort? Well, the effect of that effort is to change the kinetic energy of the object. Okay? So whenever we have a system like this, and it's got some energy, and if we transfer some energy to that system, then the energy of the system will increase by the amount that we've transferred. That's just conservation of energy. Okay, so what this is saying is that is that the work that we've done, the effort that we've put into the system, the effect has been to increase a certain form of the energy of the object inside, which is the kinetic energy. Okay, and so this makes total sense. And so really this thing work, and this is a super important point, this thing work, this thing effort expended, what work really means is the energy transfer. And that's what we're starting to talk about now, is energy transfer mechanisms. And the simplest mechanism by which you can transfer energy from one system to another, or from one form to another, is to apply a force acting through a displacement, and that transfers, in this case, kinetic energy, because we're just acting on a block whose only way of storing energy is kinetic energy. Okay, so this is yes, this definition makes sense. Okay, and it identifies work as a energy transfer mechanism. So work is equal to energy transferred. Okay, great. What else should we say? Oh yeah. So now you say, well, okay, let's see. So we have transferred some energy to the system, which is the block. We've transferred kinetic energy to it. Well, we know that total energy is a conserved quantity. So if the energy of one thing went up, namely the block, nature has stored more energy in the block. Well, then the energy of something else must have gone down, because energy is always conserved. Okay, and so we say, so 0 is equal to the change in the total energy. So by total here, we mean of the total system. That includes the block, which has gained some kinetic energy, and what else is in this whole thing? The person. So obviously the person has lost some energy. Okay? So it's actually a little bit more interesting and complicated than this. So what we say is, yes, what are the various ways, when we try to apply this principle of conservation of energy in the form of the total energy of an isolated system remains constant, the first step we need to do is think a little bit about what are the various ways in which energy is being stored in this whole thing, block and person. Okay? Well, one of the ways that energy is being stored here is kinetic energy. Okay? And that kinetic energy obviously has changed. In fact, it has increased. Okay, so there's been a change in the kinetic energy. So, and that in fact change has been positive. The kinetic energy has gone up somewhere in the system. This block has gained some kinetic energy. Something else must have lost energy. And so this person has different forms of energy. And so there's chemical energy, for instance, which of course we know is just a form of electrostatic field energy between charged particles inside your body. So there's some chemical energy, and that has also changed. So after this guy does a bunch of work all day, this guy's got to eat. Okay, so the chemical energy in that person has gone down. The change in the chemical energy of the person is negative. Okay? But there's also something else here, and that is after this guy does this work, right? Human beings are not very efficient machines, and so they heat up and they sweat. Okay, I've done lots of work. I'm really hot now. And so there's also a change in thermal energy. So there's thermal energy in this system, and it has changed in this person. It has gone up. There's been a change in the thermal energy, which is positive. Okay, so in this system, there are three kinds of energy involved. There are three different ways in which nature is storing energy. Kinetic energy in the block, chemical energy in the person, thermal energy in the person. Okay, and so when we write the total energy, it's kinetic plus chemical plus thermal. And so the change in the total energy is a change in kinetic plus change in chemical plus change in thermal. And all three of those changes better add up to zero. So if one of them is positive, or here two of them are positive, one definitely has to be negative so that the whole thing adds up to zero. Okay, and so what's happening here is this change in chemical energy. I don't know, maybe it's negative 100 joules. Okay, so this guy's burned through 100 joules of chemical energy. Okay, and you need to eat like muffins worth 100 joules of energy or whatever to replenish his energy. Okay, and maybe the kinetic energy of the block has increased by say a certain amount, say I don't know, like positive 20 joules or something like that. Okay, then the thermal energy must have increased. This person must have heated up their thermal energy. Their atoms are jiggling more vigorously and so on. It must have increased by plus 80 joules. So that this 20 joule increase in the kinetic energy of the block, 80 joule increase in thermal energy of the person is compensated for by a 100 joule reduction in the chemical energy of the person. So that 20 plus negative 100 plus 80 is equal to 0. Okay? So two ways to think about this situation. Transfer of energy. We've transferred energy from this subsystem to this subsystem, okay, through work done. Work is an energy transfer mechanism. Or we can think about it as conservation of total energy in the sense that the energy of an isolated system never changes. Just identify all of the forms involved, all the forms of energy involved in the system, and make sure that their individual changes add up to zero. Some will be plus, some will be minus, such that the total change, the change in the total energy is equal to zero. Okay, very good. Okay, so we're on the topic of energy transfer mechanisms. We've talked a little bit about work as a mechanism whereby nature can transfer, say, for example, chemical energy in my body. I apply a force acting through a displacement, and I transfer chemical energy in my body into kinetic energy of the block that I'm accelerating. That's just one example of an energy transfer mechanism. Nature is full of all kinds of amazing energy transfer mechanisms. And another one that's very important, and is given a special symbol, W is for like work, force acting through a displacement, is Q, given its own symbol Q, and that's heat. So heat is the transfer of thermal energy, the transfer or flow of thermal energy. Transfer or flow of thermal energy. Okay, so you put a hot object next to a cold object, thermal energy is transferred from the hot object to the cold object. I want to distinguish between thermal energy, which is a way that nature can store energy, and heat, which is a way of transferring energy. Storage and transfer are different things. Okay, so let's look at there's three different ways in which this can happen. The simplest possible way in which it can happen is you take a block that of some substance which is hot, and you put it in direct physical contact with a block that is cold. And so this is heat transfer of thermal energy through direct physical contact. Okay, so you know, obviously what's going to happen is this hot object will cool off, its thermal energy will decrease. At the same time, this cold object will warm up, and so its thermal energy will increase. So there's obviously been a transfer of thermal energy from the hot object to the cold object, and that transfer of thermal energy is the amount of heat. Okay, great. And so how does it actually physically happen? Well, it's very simple. So what's happening is you've got a hot object, which means that its atoms are jiggling around vigorously. Okay, so here's an atom right near the surface of this hot object, and it's jiggling around vigorously. Okay, and it's in direct physical contact with an atom in the surface of that cold object, which is jiggling less vigorously. So here you have a fast-moving object, bang, hits a slow-moving object, and there's some kinetic energy transferred from the fast-moving object, this one, to the slow-moving object, this one. So then this one picks up speed, this one gains some kinetic energy, and so now it's moving faster than its neighbors. So it transfers kinetic energy to its neighbors and so on. So like dominoes. And so then that extra kinetic energy flows through the cold object and gets distributed. And the thermal energy of the cold object goes up while this guy is now moving slightly more slowly, so the hot object next to it is going to make it move fast again, and so this guy cools off, and so the coolness, so to speak, the less vigorous jiggling flows this way, moves this way, and the more vigorous jiggling moves that way, until eventually they reach thermal equilibrium where they're at the same temperature, and then, you know, randomly there'll be some energy transfer that way, but an equal amount that way, and so eventually there's no net energy transfer, so the heat stops, the heat flow stops, and they've reached thermal equilibrium. Okay, so that's a way in which thermal energy can get from a hot object to a cold object by direct physical contact. A second way, which is a little bit more interesting, is you just take these two objects. You don't have to touch them together. Okay, all you got to do is take a hot object like this. Okay, you don't touch them together. Put it next to a cold object like this, and we'll imagine there's no air here, just to keep things as simple as possible. This is occurring in vacuum. Okay, and so you wonder, well, how can there be any transfer from this hot object to the cold object? Well, the answer is, remember that material is made out of positive and negative charges, atoms and so on. And so a hot object, these positive and negative charges are jiggling around, which means that they are accelerating. Okay, they're changing their velocity, either direction or magnitude. And a super important fact to understand about, and you'll learn this later, I guess, but super important fact to understand in general is that the source of all electromagnetic radiation in the universe is accelerated electric charge. Okay, so, you know, if I take a positive charged particle like this, and it's moving slow at first, and I make it move fast, I accelerate it like this, it will radiate photons. Okay, light will come off of this thing. Okay, it's just like a radio. It's like an antenna. And you have, you know, electron in there, and you make that antenna in your cell phone, you make that electron, you know, jiggle up and down, and you're sending off radio waves, and you're communicating to the cell phone tower. So the source of all electromagnetic radiation is accelerated charged particles. Okay, and so we've got accelerated charged particles here, and so they're going to be emitting, you know, photons of random frequencies, and so on. So there's going to be random thermal photons coming off, just sort of boiling off. And so let's worry about the photons that are going from here to here. Okay, so there'll be photons which go from here to here. And so then when that when that photon hits that cold object is also made of charged particles. And photons are basically classically electric and magnetic fields. Electric fields exert forces on charged particles, so that photon grabs onto charged particles here and makes them jiggle more vigorously. And then that more vigorous jiggling then slowly sort of percolates through that cold object. And so you have that the hot object cools down, okay, as it emits these thermal photons, and so its thermal energy goes down. The cold object heats up, and so its thermal energy goes up. And so there is a transfer of thermal energy from the hot object to the cold object through thermal radiation. Okay, so this is thermal radiation. And the radiation we're talking about here is electromagnetic photons. Magnetic Okay, so you know, of course, all objects emit thermal radiation. So you can just look with night vision goggles at the objects and you can see, oh yeah, that one's warmer and that one's cooler and so on. So all objects above absolute zero in temperature emit thermal radiation. And that thermal radiation can serve as a transfer mechanism to transfer thermal energy from one object to another object. Okay? So that's sort of the second mechanism. And the third mechanism is called convection. And so the idea is, okay, so this happens, for example, all the time in just the air. So, you know, the sun hits the ground and warms the ground, and so then the air near the ground warms up. And so we have like a parcel of air over here that has been warmed up. Warmed up means it's got more thermal energy. The atoms are jiggling around more. They're moving with greater velocity. And then, the wind blows. So it takes this parcel of warmer air, okay, and it moves it, physically moves it from here to here. Okay, and so there's been thermal energy moved from here to here. So that's transfer of thermal energy from one location to another location, and that's called convection. Just sort of the mass transport of warmer molecules or atoms from one place to another place. Okay, so I guess a nice example of this is just to do with the sun. So this is the sun, and at the core of the sun, we've got these thermonuclear fusion happening there, and the process of fusing hydrogen into helium that produces one of the particles it produces is very high energy photons. So these very high energy photons coming out. Okay, and so that thermal energy wants to get out. And the way that it gets through the material of the sun is at first through radiative. So this region of the sun, from the core to, I think it's about 70% out, in this region you have photons. So thermal energy is being transported from the core outwards by radiation. So this is radiative transport of thermal energy. Okay? And I should just mention that, of course, inside the sun is basically a great big ball of hydrogen gas, and the hydrogen is a proton and an electron, okay, but it's so hot that the atoms of hydrogen are ionized, and so it's basically a gas of protons and electrons. So it's electrically neutral gas of charged particles. Okay, and these photons basically, snake their way through those charged particles, bouncing off of them, and so on. And then there's radiative transport of thermal energy. But when it gets to this layer of the sun, then the thermal transport, the heat, the transfer of thermal energy changes from radiative transport, to convective transport, convection. Okay, so this is really cool. This is exactly like boiling water. So we have, here's a pot of water on the stove. This is a hot surface. Okay, and so there's thermal energy going in. It heats up the molecules of water down here. When as you heat something up, well, the atoms and molecules are jiggling more vigorously, so they require more elbow room, and so the material gets less dense, and so then it rises up. Okay, and so you have like less dense region, hotter molecules rise up like this. They come to the surface here. They radiate their thermal energy. They cool off. They become more dense and they fall back down. Okay, and so what you get are convection cells like this. In boiling water, if you just watch boiling water, you can see these convection cells at the surface. The sun is exactly the same. So the hot source down here is this radiation of hot photons coming up like this, and it's basically hitting plasma here in this layer at the bottom, and it's heating it up. So that plasma, those charged particles, plus and minus charged particles, get protons basically, they get heated up, and so then they need more elbow room, they get less dense, they rise up. So they rise up like this. Okay, and then they come to the surface of the sun, and then they're charged particles, and they're jiggling, and so they emit thermal radiation. Okay, and so they emit photons. And so the photons that we see when we look at the sun and that lights our world are not the photons created here in the core. They are the photons created right at the surface of the sun. Okay, because that's a hot surface, charged particles jiggling around, radiating thermal photons coming off like this. Okay, and so that hot parcel of plasma comes up, radiates its energy out into space, and it cools off, becomes more dense, and it falls back down. And then it's reheated, and it goes back up and falls back down. And so you get convection cells, exactly like for boiling water. And so the surface of the sun, when you look at it, it looks exactly like boiling water. because it's the same thing. And so there are convection cells. You can see them. It's super cool. Look at a picture of, on Google, just look at a picture of the surface of the sun. You can see these convection cells. So this is a nice example of convection. Okay, so all of these methods of heat energy, transfer of thermal energy are important and interesting and apply like in all kinds of places. So it's a good idea just in the back of your mind as physics students of physics to have a feeling for the idea of transfer of thermal energy or heat. Okay?